Hey, so welcome back, everyone. This is the Foundations of Quantum Mechanics lecture series. So just to quickly recap, last time we were talking about the measurement process in quantum mechanics, and especially how we have this picture of branching and different mutually incoherent branches. Just to recap this a little bit, this is the kind of picture we might have in mind, where in each measurement we really go into one of the, say, two different branches. If there are two measurement results, and if there is a subsequent measurement, then we will branch again and again and again. For each measurement there will be a branching. So there will be something like a tree. And just to remind you a little bit, for each of these branchings, we saw that one thing that does happen is there is entanglement between the system state, here the spin, and then the apparatus state, here high up and high down. So that's one thing that's going on. We have two different pointer states, high up and high down, which quickly will become orthogonal if it's a good measurement. So that's another thing. But this is not enough. In the end, these pointer states also need to get macroscopically distinct so that it is not easy at all to undo the measurement. And this is here reproduced by all these little arrows that represent extra particles being scattered, or photons being emitted, or electrons being released. And this will lead to macroscopically distinguishable pointer states and to some irreversibility. And once it is truly irreversible, then we will never see any interference effects anymore between these two parts of the wave function that in principle are still in a superposition. But for all practical purposes, we can now treat them like separately. So each of them we can claim for all practical purposes is just one or the other quantum state occurring with a certain probability, as if these were two classically different possibilities. And once this is true, then within each branch, we can just pretend that there is only one wave function, not the superposition state, only one wave function, and we can continue with the time evolution of this one wave function. And that is, of course, exactly the description that was previously known as the collapse of the wave function. So here we have an idea of why this collapse comes about. Also in this way of describing things, everything is the Schrödinger equation, everything is unitary time evolution. In principle, there's nothing discontinuous. And this collapse, so to speak, is really only a discontinuous change of our description and not something physical. Okay, so now I want to go on and discuss a few further aspects of measurements. And the first one I want to spend some time on is so-called weak measurements. I'll try to explain what that is about. In the end, this is really about getting a bit more realistic and looking at how a measurement in an actual device nowadays would be going on. And in the end, it will give us a way to think of time resolving the details of such a measurement. And I want to compare it. In principle, there's no new concept here. It's just slight change in perspective. On the left-hand side, you see our standard measurement setup that we've discussed so far. So think of the Stern-Gerlach experiment. We have the two branches. At first, you could say the overlap between high up and high down goes to zero. And this happens already very early. We know that in the Stern-Gerlach apparatus, in the first moments, what we have is simply the spin direction will affect the force acting on the particle, and the particle will be pushed up or down depending on the spin direction. And so we get an entanglement between spin and the motional state, so the wave function in position space. And this alone is already enough to give us this orthogonality between the two pointer states, which are now the two wave functions in position space. And only after that, this is amplified when the particle hits the screen and we have this whole detection process going on. Then out of that will evolve two really macroscopically distinct pointer states, and we have the irreversibility. Now, when we switch to describing a weak measurement, what we imagine is really that both of these things go on at the same time. So the irreversible accumulation of information and the two pointer states becoming orthogonal, that is going on at the same time. And I will make it very clear in an example how this looks like. So how might this look like? Here's a very typical example, which is of high practical relevance, because this is what goes on in many modern experiments of the type where you try to build elements of a quantum computer. You need some way to actually measure one of your qubits, one of your two-level systems. The two-level system might be implemented in the form of an atom. This atom then can be subjected to a light field. So you can shine light on the atom, and depending on the state of the atom, there will be slight differences in the light that is scattered from the atom. And from these slight differences, you can determine which was the state. So to make it even more clear, here we imagine a situation where the atom is really placed in a cavity, so between two mirrors. This just increases the strength of the interaction between the light beam and the atom. And so we have an incoming light beam. It interacts with the atom, and when it goes out on the other end of the cavity, it will have acquired a phase shift. And it is in this phase shift that we have information about the state of the atom. For example, you might think that the phase shift has one sign or the other sign, depending on whether the internal state of the atom is one or the other internal state. And we will continue to call these two states up or down, just because that's the notation we have already gotten used to. Okay, so two different phase shifts depending on the state of the atom. Now, if we look, however, at these things in more detail realistically, we realize that the phase shift is not just this signal, this clean signal that does depend on the state and has only two different values. What we have in addition is noise. And this is not some technical noise, rather it is some fundamental noise. Because on each beam of light, on each laser beam, I have what is so-called shot noise. So shot noise can be explained in many different ways. Some people like to say, if my laser beam in a certain time interval has n photons, there will be fluctuations in the photon number plus or minus square root of n on this order. So that's one way of describing shot noise. You can also say that besides the classical part, the deterministic part of the strong amplitude of this laser beam, of this light field, there is still the vacuum noise that is always there in any electromagnetic field. And so there's another way of describing this shot noise as, so to speak, the interference between the strong classical clean signal and the vacuum noise. In any case, there is noise, and that's the important point. So there will be signal and noise. And so now if I draw for you a picture of the phase shift that you could detect further on with a suitable measurement device as a function of time, then it looks like shown in the picture here. And I've already drawn it for the two different possible states of the atom, either the blue, the up state, or the red, the down state. And you see that the phase shift for these two cases has a different average value. That's the promised signal that has two different values depending on the state of the atom. But on top of this average value, there is noise. And it really looks like this. So there have been experiments that literally take time traces like this, and that is what they observe. Are the different phase shifts caused by the difference in energies of the two states? So what one can think of, it's less a difference of energies and more something else. I can try to explain it. So if I have an atom, say with just 2 levels, famous 2-level atom, so to speak, I could be either, say, in the lower state, or I could be in the higher state. And now I can ask myself, if I were to have not only one atom, but many of them, and they form a kind of medium, something like a glass through which light can be transmitted, what is the refractive index that the light sees when it goes through this medium made of these atoms? And it turns out that the refractive index that the light sees is different for this state, let's call it the down state, than for that state. You can even do a detailed calculation. So in this quantum mechanical calculation, you would start either from the ground state, then go up with your incoming light field to some virtual state. It's a little bit detuned, maybe even from the upper level, and then you go down. Or if you are in the upper state, then the situation is different. And so you will see a different refractive index. And that remains true even for a single atom. So we can say the light sees a different refractive index, and therefore it sees a different phase shift. Okay. The details here are not important. I'm not going to write down the details of the Hamiltonian and go through this. This is more a quantum optics problem. But what is universal here is that the signal you get, the phase shift in this case, is composed of a clean average part that really depends on the state, and some noisy part. There are other cases where instead of having, say, this light beam, you could have a current running through a wire. And then if you have next to this wire an electron, it will slightly repel the electrons that are trying to make up the current and block the current to some degree, so the current will be lower. If I move the electron to the other side of this little double well potential, then the electron is further removed, the current will be higher, and so you get 2 different currents. And again, the same thing applies, namely, there is a difference in the average current depending on the discrete state of the quantum system, but in addition, there will be noise, current shot noise. Okay, so these are details, but remember this picture. So there's the average part and the noise. And now we want to discuss what is the consequence of this. The noise prevents me from immediately identifying the state. Because if I'm only allowed to look at, say, the first short time interval, this one here, and I observe a certain trajectory, but of course it's not colored blue or red, no one is telling me what is the actual state, I just see this noisy trajectory, then I cannot be certain, even if the values are a little bit higher, I think, than usual, I cannot be certain whether that means it is indeed the blue state, the up state, or whether maybe this is just a statistical fluctuation. I'm really in the down state, but it's a statistical fluctuation towards higher values. So how to come to a unambiguous determination of the state? Well, the idea is you need to time average, because if you time average, you will average away the noise and you will be left with a clean signal, and that will really tell you which state you have. Now, that concept is clear enough. If I time average or take the integral over theta over time, which is equivalent, then I see something like the following. So let's draw this time integral of theta versus time. How does it look like? Well, I try to draw that here. The integral of the phase over time. The lowest order description of the resulting picture is, of course, you get a linear increase in time. Why is that? Because theta has some average constant value, and that gives you the linear increase of this time integrated signal. But then on top of that, of course, there's a contribution coming from the noise. And if you know a little bit more about physics, maybe from your statistics lectures, if this noise, for example, would be white noise, that is, the values are completely uncorrelated at different moments in time, then the integral of this white noise in theta will be actually a random walk, a continuous random walk. And so this is what I'm showing here, a linear increase, and superimposed on top of that a random walk. Now, the one important point here is the following. The signal, the thing that distinguishes up versus down, increases linearly in time. The noise, that's this random walk, the typical spread of the noise away from the linear signal trajectory, that only increases like the square root of time. That's a typical thing for a random walk. And so what you see here is the following. At early times, it is indeed very hard to distinguish the two, because you can never be quite sure, am I looking at one trajectory or the other? Is it only a statistical fluctuation that makes the values a little bit higher than expected? But up here, at later times, it's very easy to distinguish these two trajectories, even in spite of the noise, because the distance between them grows linearly and the noise only grows like the square root of t. So eventually you have enough resolving power, so to speak, to distinguish the two states. And that's the main thing you should understand about weak measurements. Just wait long enough, time average or time integrate, and you will be able to distinguish your two states. And this is the way that you can really describe a measurement process not as a one-step thing, but as a continuous in time process where slowly but surely you learn more about your state and eventually you are able to, for certain, resolve one state versus the other. That's the idea. Now, we can come back to our language of pointer states. This still applies here. So these pointer states would be states of the whole light field, of the electromagnetic field. And sure enough, their overlap goes to zero. So this is one thing that happens if you just wait long enough. And it turns out that the way it goes to zero, and we will describe it a little bit more in the rest of this lecture, is tightly related to this information gain. So as your difference in the observed integrated signal becomes larger than the noise, and you can really tell for sure which state you're looking at, it is at this moment also that the overlap must have gone to zero or is close to zero. Okay, so this is a very shortcut description of weak measurements. If you're interested in how this is technically described, how you could do a calculation, how you could even do a simulation on the computer of these noisy measurement signals as they would be observed in experiments, if you are interested in all of that, which is a very interesting topic, then go look in a standard modern quantum optics textbook and look for the keyword of stochastic master equations. So these are the equations that describe this noisy measurement signal. Okay. Now, I don't go through the technical details of these stochastic master equations, but still I want to resolve this a little bit further, and I will do it by simplifying it to the bare essentials. So the first simplification you could make, I think, okay, so there's a new question, so maybe I should go back. Could you please give a quick hint about the source of that noise? I think it will become very clear in what I'm going to describe now. So I think that's much easier than me trying to just describe it in words now. But again, it's the shot noise. If you think, for example, of not photons, but an electrical current, then it's also known as shot noise. So even if the average current is, say, 1 million electrons per second going through your wire, then if you do measure the amount of electrons that have passed through your wire in 1 second, you will not find precisely 1 million. You will find something like 1 million plus or minus 1,000 electrons, typically. And so this is the noise, very simple noise. Okay, but I think it will become much clearer if I describe it in detail here in the simplified picture. So the first simplification you could make is, instead of looking at this continuous beam of light, you could split it up into many different wave packets that impinge on this cavity that houses the atom. And each of these wave packets, as they have passed through the cavity, will then have acquired a little bit of phase shift. So that's already a simplification, because you have these discrete wave packets, the string of wave packets. Even simpler, you could say that instead of these wave packets of the electromagnetic field, let me just consider the simplest possible quantum system that I could have. For example, let me just consider a single two-level system, or a single harmonic oscillator, if you like, which is then already close to the wave packet picture. So in any case, this is the most simplified picture that you can think of. You now have a stream, a discrete stream of quantum systems passing by your atom, and they will be used to describe the measurement. We call them ancillars. This is a little bit modern language coming also from the field of quantum computation. They are helping us in a sense. So they are not the main object of interest, which is the atom, but they are helping us to interact with the atom and learn something about the atom. Okay, so now how does this work? Let's just look at how the overall quantum state of this whole system looks like and how it evolves. The overall quantum state involves both the quantum state of the atom and all these ancillars. So at first, we have what I've written down in the first line. We have a superposition state for our atom, as usual. That's the starting point of our story all the time. And then we have, independently of that, that is as a product state, the initial states for ancillar number 1, ancillar number 2, ancillar number 3, and so on and so on. Okay? Then we imagine that ancillar number 1 has passed by the atom and has experienced a brief interaction. Its state has been changed slightly depending on the state of the atom. That might be something like the phase shift I've been talking about, but our description is completely independent of the nature of this interaction. So now, importantly, and just as before, this is no new story for you, you get the state of ancillar number 1 depending on the state of the atom, so either up or down. The other states of all the other ancillars, they are still independent of our atom, and so these are all just in a product state. And so this happened to the first ancillar, then I can do it for the second ancillar. And again, I will find that after the interaction, the second ancillar will now also be in a state that depends on whether I'm up or down in the atom. The rest of the ancillars, as usual, is still in a product state. And so this would go on and on. So each time an ancillar passes by the atom and has its brief interaction, we get more states on the left part of this expression where they are correlated with the up versus down. And we have fewer states in the rest of the expression where they are still uncorrelated. So that's the idea. I hope this is clear. I mean, it's a very simple extension of what we have said before. It's just like many measurement apparatuses interacting with our quantum system one by one. Okay. And so why do we call this a weak measurement? Well, we will call it a weak measurement if this overlap between the state of the ancillar after the measurement for up versus down, if this overlap is still close to 1. Before the measurement, these were the same states, so the overlap was 1. After the measurement, they are slightly different, but not too much, and then we call it a weak measurement. That does not mean that after many ancillars have passed by, it is still weak. Then it can, so to speak, slowly evolve into a strong measurement where we know for sure whether it's up or down. It's only from the point of view of each individual interaction that this is weak. Okay. Why? So there's another question. Why is there a preferred basis for the pointer states? Why isn't all of this happening, for example, in the left-right basis instead? You mean instead of up versus down, I could consider up plus down versus up minus down? Yes. Okay. Now, this is just because of the way I imagine the interaction to look like. So I imagine an interaction that changes my ancilla depending on whether I'm up or down in this basis. If I set up a different interaction, then there will be a different preferred basis. So it depends on your interaction. That's the point. And we are here looking at the simplest possible case. This, of course, has nothing to do particularly with the weak measurements. This was already true before. So we always picked a particular basis and said our measurement device is constructed so as to be able to distinguish these two basis states. That was then our measurement basis. And we always called it up versus down. If you wanted to distinguish up versus down in the x direction for the spin, you would have to construct your device slightly differently, and then that would be the preferred basis. I can choose an arbitrary basis to do the description independently of the interaction. That is in principle correct. But the problem is then that things start to look more and more complicated, because then, so to speak, instead of having, so the problem will be, I like to keep separate the term with the alpha times something and the term with the beta times something. And if I'm choosing the right basis, then the up state will never be scrambled by the interaction. It will always remain the up state, and the down state will always remain the down state. And especially for a description like this, where I want to have repeated measurements, it's very important for me to have such an economical description. Otherwise, this would look more and more complicated as time goes on. So this is why I prefer this basis. Another question, so for the strong measurement, that inner product should be 0? Yes, so then we would call it eventually a strong measurement. Okay, so now I want to briefly say how we go from the weak to the strong measurement, since you already bring it up. What I've been talking about here was the overlap between the up versus down state for an individual ancilla. Now we can talk about the state of all of these ancillas together. So the full state of the measurement apparatus, so to speak, which for us is the string of ancillas or the string of wave packets, or more realistically, the full state of the electromagnetic field in that more general case. How can I represent it? And what we see directly from the formulas that we were just discussing is, if we pick all the ancilla systems that have already interacted with the system, they do start to become dependent on the quantum state of the atom. So in this case, I say the quantum state is up, so they are the ancilla states that I get when the quantum state is up. For all the other ancillas that have not yet interacted with my quantum system, they are still in their original state. And so if the subscript here is really a discrete time index, then say larger times are those ancillas that will interact later, so they have not yet interacted here. And smaller times, so here t prime less than or equal to t, those have already interacted. So this is why they are in this first product of states. Okay, but overall, the full state of the measurement apparatus of the string of ancillas is a product of many states, some of which are already dependent on the state of the atom, and many of which are not yet depending on the state of the atom. And now that's a good thing, because if I now want to calculate the total overlap between these two overall full states of the measurement apparatus for up versus down, what I find if I plug in these kinds of expressions is that all the overlaps of the ancillas that have not yet interacted, they are one, of course, because it's the same state regardless of up versus down. Only the overlaps for those ancillas that have already interacted with my quantum system they are not 1, and so I need to keep them. So this is what's written down here. So I have a long product, a product of many factors. And now I can imagine the following. Let's say the interaction is always the same for each ancilla. Also, each ancilla has been prepared in the same initial state. So what I then expect is the chi up and chi down for each ancilla. That's actually the same things regardless of the ancilla. So also the overlap will always be the same. So the overlap is a number of magnitude less than 1, but the same one for each of the ancillas. And so as time goes on, this product that I'm evaluating here is just longer and longer, and is just this number to the power t. And if I happen to call this number e to the minus gamma, and no one can stop me from doing this, then if I take this to the power t, remember t is here a discrete time, then I just get e to the minus gamma t. And that's very nice because it tells us, aha, this overall overlap between the two full apparatus states, that really decays to 0, and it decays exponentially to 0. So it has a very simple time dependence. And eventually here at very late times, I could claim the overlap is basically 0. And that's when out of many weak measurements, I have overall really done a strong measurement. And so we also nicely see how this happens at this, how this overlap goes down at the same time as the number of degrees of freedom, the number of ancillas that are involved in this measurement process goes up. So the irreversibility and the overlap going to 0, and then later also the information gain, they all happen at the same time, at the same rate. Okay, good. I still didn't discuss one thing. So I put a lot of emphasis now on how this overlap goes to 0, but I started this discussion of weak measurements by saying something about this measurement trace. Remember the phase shift and the time integrated phase shift signal and all the noise and so on. And then you asked, okay, where does this noise come from? And this can also be seen very nicely in the simplified model. So what we are now discussing is, so to speak, the measurement trajectory, the actual outcome. And in order to grasp this, you have to imagine the following. Yes, there was this interaction of each ancilla as it passes by the atom. So the ancilla has now become entangled with the atom, and it has learned a little bit about the atom. But in order to translate this into an actual measurement signal, something that we can write down, at some point in our description, we still need a strong measurement, and we need a definite outcome, so to speak. And so the idea in all of the description of weak measurements, the general idea also for stochastic master equations, is very simple. Namely, you take your ancilla after it has interacted with the atom, and you send it to a detector, which can carry out a strong projective measurement of the ancilla state. And so the idea now will be the following, and we can discuss it in more detail in a moment. The idea is the ancilla state will be changed only very slightly by the interaction, because it's a weak interaction for a brief amount of time. And so even the strong measurement, it will not reveal too much of information. Each individual strong measurement of an ancilla will not reveal too much of information about the atom itself. Only if you do many of those strong measurements, you really learn something as time goes on. So let's see how this really works like. Let's assume I have found a suitable measurement basis in the Hilbert space of the ancilla. Yeah, so that basis, which I call 0 and 1, is really in the Hilbert space of the ancilla. If the ancilla are two-level systems, well, then it's just suitably chosen two basis states there. Otherwise, it's something more complicated. And then if we do a projective measurement in the spaces, we want to know what are the probabilities to get 0 versus 1. And it turns out, since the chi up and chi down are different states, if you don't choose this measurement basis in a completely stupid way, then there will be a difference in the measurement outcomes for chi up versus chi down. So if I apply this projective measurement of the ancilla, and the ancilla is in the state, no, I should not mix my colors, is in the state high up, then we might see the probability distribution shown here. So what this is just the projection of high up. Okay, that's high up for a particular ancilla. So I need to be a little bit careful with my notation. So maybe that's ancilla number J, I don't know, up. And then I project it onto the zero state and I take the square of this. This is the official way in quantum mechanics to calculate the probability. So that's represented here by this bar diagram. And correspondingly, there will be a probability to find one. And I here just assume that it is larger. Now, if I go to the high down state on the right-hand side, these probabilities will in general look different, and maybe the probability to project into the zero state will happen to be larger. And so that's very important, that these probability distributions of my ancilla are different depending on whether it ended up in the high up or high down state. And so now if you go ahead and not only do this measurement once on one ancilla, but many times, you will see trajectories like the ones shown below. So for example, in the case that we are in the up state, so I observe high up and project it onto 1 or 0, you see that the probability for getting 1 is larger than for getting 0. And so that means if I now look at a typical random realization of my string of measurements, I will see more ones than zeros. So 1, 1, 1. There are many of those here. And correspondingly, if I'm in the down state, the probability of finding 1 is less. And so correspondingly, I will see more zeros. And so this, what I'm showing here, is basically a discrete version of the shot noise picture that I was showing before. Yeah. And now you can see the idea again, just like before. If you only look at a few of these projective measurements of the ancillas, and you observe 3 times 1 and 1 times 0, yes, there is maybe some evidence that maybe we are in the up state, but you cannot be quite certain because everything is random anyway, and maybe it was just pure luck that you got so many 1. So you really have to look at longer time spans and do averages to finally be fairly certain whether you are looking at up versus down. Okay. So I want to pause here and ask whether there's a question about the weak measurements. It was a little bit fast because I still have many other exciting things to tell you. But this is the basic concept. So all of these stochastic master equations and so on, they start from the same basic concept. And then basically what they just do is they take a continuum limit where these interaction time intervals get shorter and shorter, and then you get more and more steps in a given large time interval, and then you take a limit and you get a fluctuating continuous signal. Yes, this noise is essentially quantum mechanical. Here you might call it projection noise in the sense of, okay, I'm doing these measurements and I get a discrete outcome, 1 or 0, and so people sometimes call this projection noise because you do a projective measurement. But the same physical concept applies to the shot noise that I discussed earlier. And also there already, this is a purely quantum noise. It's a pure quantum state. It's not a thermal state. These are not classical fluctuations. And there are also ways of presenting the shot noise of a laser beam in a language that makes it look very quantum mechanical. So as I said, it can be viewed as the interference between the large, so to speak, classical signal, the large amplitude, classical deterministic amplitude of the laser beam, and the vacuum noise. And the vacuum noise, of course, is something very quantum mechanical. Okay, good. So I let that sink in. In the continuous limit, the overlap becomes a path integral. I guess, yes, I can write it like this. So the point is, Okay, one has to be a little bit careful. So this overlap, there's no need yet to represent it as a path integral. But I guess if you try to represent it in terms of the measured trajectory, then you will end up with path integrals. Yes. There's another question. Is the amount of information obtained about the system with this type of measurement the same as in a destructive measurement? Well, we can only compare the final outcome because the destructive measurement, so to speak, goes from, and we should also be careful a little bit about our language. So I think with destructive measurement, you mean an immediate projective strong measurement, right? And then we can only compare the final outcomes. And then, of course, the answer is yes. So strong projective measurement, I immediately jump to the end. Weak measurement just means I really resolve what goes on in between, but the final outcome is the same. Oh, why would one do weak measurements? Well, the reason is often you have no choice. I mean, this is what I'm showing here. This is what is happening in real experiments nowadays. Of course, the aim will still be to do a strong projective measurement of your qubit, but you cannot have it instantaneously. You need to send this measurement beam, which has a finite intensity for a finite amount of time through your system to slowly acquire the information you need. I mean, slowly is of course relative. Maybe a few nanoseconds are enough, but still conceptually you can resolve this and see really how this doesn't happen in an instant, not immediately, but over a short amount of time. So there's a second suggestion for a possible answer to this. Maybe you do not want to disturb your system. Well, one must say the following here, and that's maybe a very important thing, also going back to this mention of destructive measurement. What we are looking at is already the best possible measurement that one can do, in the sense eventually up will be distinguished from down 100%. Also, I don't scramble up or down. The up state doesn't flip into the down state during the measurement. So this kind of measurement that we are describing here is also called, and I should maybe have emphasized this, quantum non-demolition measurement. So what this means is exactly what I said. You don't scramble the spin during the measurement. What this also requires is that there is no extra Hamiltonian that will lead to some precession that can turn up into down while the measurement is going on. So the measurement operator, which here would be sigma z, the spin along the z direction, if that is our basis, this measurement operator that we are measuring commutes with a Hamiltonian. Now, non-demolition means, so to speak, non-destructive in a sense, but it's just as non-destructive as it can possibly be. What is always true is you eventually lose the coherence between the up and the down state. So if there had been an interesting phase difference, so alpha and beta are complex amplitudes, and there could be a phase difference between them, and you could see that in an interference experiment if you don't measure in the up versus down basis, but some other basis. This phase difference eventually will be unimportant, and we are going to discuss this just in a moment. And so this is still destroyed, so you can never avoid that in a measurement. You can never avoid destroying superpositions, but at least you can avoid destroying even more about the state. So yes, the perturbation here is as small as it must be. This is the proper way to phrase it. Okay, another question. If we write the state as alpha times 0 plus beta times 1, can we say that the weak measurement just changes alpha and beta for each ancilla? I think I don't quite know what you mean. So for me, alpha and beta are just the amplitudes for the initial superposition of the system state. They will never change. And forever after, there will be two pieces of my overall wave function, even though it gets complicated. One piece has the prefactor alpha, the other piece has the prefactor beta. So maybe I still don't quite know what you mean. Oh, okay, so different. Different amplitudes. Okay, so that have nothing to do. Well, yes. So what I can certainly do, and I didn't go into the details here, I could choose to represent my ancilla state in some suitable basis, and who knows if I'm in the end anyway want to measure. If I want to measure in this ancilla Hilbert space 0 versus 1, I might as well take this basis. And then it would look like some amplitude times 0 plus another amplitude times 1. And then its interaction with the atom will change these two amplitudes, but the change will depend on whether the atom is up or down. And that's a proper description, of course. Yes, that's true. Okay, good. So now I want to move on. This was weak measurements, or a series of weak measurements, which eventually gives you a strong measurement. I now want to discuss something that goes more in the foundation, in the real foundational aspects, and actually goes back to an aspect of Bell's inequalities, or it's even something like a cousin of Bell's inequalities. So what we now want to consider is the so-called Leggett-Garg inequality. But another way to put it is we are looking at non-commuting measurements and time order. So, and the goal will be a little bit similar to what we did for Bell's inequalities, namely by looking at statistics of measurements, the correlators of measurement results, we can rule out a certain class of hidden variable theories. But instead of having two quantum systems that are entangled, now we want to look only at a single quantum system. So we have to proceed differently. Now, one particular feature that is very peculiar to quantum mechanics is that the outcomes of measurements very strongly depend on the order of measurements, at least if you're trying to measure non-commuting observables. So whether you first measure X and then you measure P, or the other way around, makes a big difference, because the first measurement, as we know, it changes the state of the quantum system. For example, if I measure P, I know this has, if I measure it to high precision, it has to completely scramble X, or if I measure X, it has to completely scramble P. And so the subsequent measurement will then reveal different outcomes depending on what went first. And this is true not only for position and momentum, it's also true for spins. For example, if you measure the spin at in the X direction and then in the Y direction, or the opposite order, it's the same story. Also, you can do other tricks. For example, you can say, I have measured my spin, say in the X direction at time t1 and at time t, let's call it t3. So this is what happens here. And if there was no Hamiltonian acting in between, so no precession going on, I might even have recovered exactly the same value in the second measurement, okay? But now if I choose instead to insert another spin measurement in between, for example, in the Z direction, which does not commute with the SX operator, then I will again completely scramble my spin and I find a different statistics of the outcomes. So outcome very much depends on order of measurements in quantum mechanics. And now we want to compare this against the classical situation, because in the classical situation, we can, in the ideal classical world, say any observable like position or momentum has a definite value at any given time. We might not know it, of course, if we haven't measured it, but there is a definite value in principle at any given time. And the second thing is, in principle at least, I could measure this observable, this classical observable, with arbitrary precision without affecting in any way any subsequent measurements. So I can measure the position, and then I can measure the momentum, and then maybe the position again, and then again the position, and then something else. And I could do this and nothing would depend on the order of measurements or how often I do this. So no influence on subsequent measurements. And now let's just assume that this is true, that we are living in this classical world or this classical-like world. Maybe the equations of motion are a little bit different. Maybe there are interesting changes there, but at least these two assumptions, A1 and A2, should hold. And we would want to derive the consequences of these assumptions. And just like for Bell's inequalities, we want to derive the consequences for certain statistics and correlators, and then see whether that's still true in quantum mechanics. So specifically, what Leggett and Garg considered in the middle of the 80s is we consider possible measurements to be done at 3 different times. So Q1, Q2, and Q3 just means measure some observables, might be different observables or the same, but at different times. And we have 3 different times. And to keep things even simpler, we'll assume that this observable can have only 2 different values. Now, if you're thinking of something continuous like the position, you might turn them into discrete values simply by saying, if the position is larger than some value, I call it +1. If it's smaller, then it's -1. So that's not really a constraint. Okay. Now, if I apply A1 and A2, if these assumptions are given, I claim that this following inequality holds that is displayed here. So what I do in this inequality is I take all these correlators, Q1, Q2, Q2, Q3, and Q1, Q3. I average the product over, so to speak, many repeated runs of this experiment. And I claim that if I add 1, I will get something non-negative. The proof is pretty straightforward. So the point is, if you consider all these 3 values, Q1, Q2, and Q3, and you think about what it means to calculate Q2 times Q3, well, that's just figuring out what's the relative sign. If they have different signs, then the product will be -1. If they have the same sign, the product will be +1. And now it's a fact of life that if I have 3 numbers, each of which is plus or minus 1, then they cannot all 3 have mutually different signs. So for example, if Q1 and Q2 are +1 and -1, then Q2 has to decide whether it's plus or -1. And I will have at least one of the links. So if I depict it graphically here in this figure here, at least one of the links will connect 2 variables that have the same sign. Maybe they all 3 have the same sign, but at least one of the links is a link with the same sign. So the corresponding product will be +1. So that means if you think about it and make a table of all possibilities, the left-hand side of this inequality will be either 0, that is when 2 of the correlators, when 2 of the products are +1 and one of them is -1. If 2 of them are -1 and one of them is +1, and overall, then the left-hand side is 0. Or it's 4 when all of the products are +1. And that holds before averaging. So the left-hand side is non-negative before averaging and therefore also after averaging. So this is a very simple proof, just as simple as the simple proofs for Bell's inequalities. And this inequality, by the way, holds in this classical assumption, regardless of whether all the 3 are measured, or maybe I only measure 2 of them while I'm trying to establish the value of any of these correlators. So it doesn't really matter. Okay, so that's the inequality. And now the goal obviously will be to find a quantum mechanical situation where this inequality can be violated. And let's not make it very difficult. We need an observable that has 2 different values. So why not take a spin or a 2-level system and then see what happens, how far we can get. So the example might be that our observable is really the sigma x, why not? And to make it interesting, I want to have a Hamiltonian that is not 0, but rather it's sigma z, basically. So what this means is I have a magnetic field pointing in the z direction. Of course, it will lead to a precession of the spin. And if you solve the Heisenberg equation of motion, I don't know whether you still know that, but that is the Heisenberg equation of motion for the spin. And if you solve it, you will find indeed what you classically expect, namely precession. So sigma x at time t can be expressed as sigma x at time 0 times cosine minus, in this case, sigma y at time 0 times the sine. So it's really like a precession in the xy plane as expected. Okay, so once we have that solution, we can now calculate the expectation value of Q, but more importantly, we can also calculate these correlators, these products. And so so that all will now start to depend on what is the initial state. I want to keep things simple. I will take as initial state this state, which is nothing but the eigenstate of sigma x for the eigenvalue +1. And then if you look at the expectation value at time 0, would just be the expectation value of sigma x in this state, which is an eigenstate, so I get +1. But as time goes on, and if you plug in the time evolution of the sigma x operator, or you evolve the wave function, same thing, you will find this cosine omega t. Now, of more interest for us is the correlator. So what is Q of t times Q of t prime? And if you go through the calculation, it would actually be the cosine of the difference in times. So what we want to have is now, we want to go back to our little inequality to the left-hand side, and we want to choose times in a smart way such that the sum of these correlators, even if I add +1, I get something negative, because that would mean that I violate my inequality. And so then quantum mechanics is different, provably different than these classical assumptions. And so it turns out one smart way to do these things is if I choose my times such that the phase difference, so omega times delta t, is always 120 degree. So I can draw these vectors if I like, and just to visualize the angles or the phases as angles. And then the correlator is always the cosine of the difference. And if I pick the difference to be 120 degree, then the cosine of that will be -1/2. And if I have 3 times -1/2, it's -3/2, +1 is still negative. So what we learn is there's the kind of distinction here, or a contradiction between quantum mechanics and this set of assumptions about how measurements could work in our classical inspired model. And this is still a large family of models. Yeah, so this was not an assumption about a specific model, but we only had these two assumptions. Namely, any observable has a definite value at any time, and it can be measured in principle without affecting any subsequent measurements. If that is true, the inequality holds, and the inequality is violated by quantum mechanics. So, hooray. Now, it might seem on the surface that this is just as good as Bell's inequalities, but I want to warn you a little bit. So Leggett-Garg is not quite as powerful as Bell, and the reason is that the assumptions are stronger. So in particular, A2, that there is no perturbation by the measurement, that's a very strong assumption. I can come up with many very plausible looking, but otherwise classical looking models, where if I measure a particle, maybe it does experience some noise because of the measurement, and then subsequent measurements will of course reveal this extra noise. So, I mean, this might even be true in actual classical measurements, because there might be technical noise coming in from your apparatus. So this is certainly a very strong assumption, much stronger than the very plausible assumptions you're making about locality and Bell's inequalities. Okay. So again, I want to pause here. Are there any questions about this part, about the Leggett-Garg inequality? This again has been tested in experiments. It's quite popular. If you, so to speak, if you cannot afford to build two quantum systems and entangle them and put them far apart and so on, this is still something that you can do. So with a few measurements, you can show that your system is definitely, at least in some ways, behaving quantum mechanically. Okay. So at the moment, I don't see any question coming up. Then I want to basically conclude for now this measurement chapter, although in a moment, actually, you will see we come back to it in a certain way. What I will now start is our discussion of decoherence. Decoherence is a very important topic. And as you will notice in a moment, we have already seen it in a disguise basically going on during the measurement. But plainly put, decoherence is the loss of interference. Before I go there, there's still one question relating to the previous chapter. So about the Leggett-Garg inequalities, if they are violated, is it still true there exists a local hidden variable theory? Okay, so now how to interpret this question. So we know we need, so I could say, okay, if I have, okay, yes, okay, no, it's a good question. So there are, or you would not be able to exclude that there are local hidden variable theories that can reproduce these results, because if there are, for example, this noise coming in from the measurement, that can easily be part of a very plausible local hidden variable theory. This noise would be local, it would be acting at the measurement apparatus where it is interacting with my particle. So yes, I could build a local hidden variable model that could try to reproduce on a single system the results of quantum mechanics. So it would also violate Leggett-Garg, but it would not be able to violate Bell's inequalities. It would have to fulfill Bell's inequalities. And so then you would, to rule out that smart local hidden variable theory, Leggett-Garg would not be sufficient, but Bell's inequalities would be sufficient. How to measure the two-time correlators? Okay, yeah, maybe I should have been more explicit. So you can work it out for yourself that even though I write it down as a two-time correlator, what this really means is please measure at the earlier time, whatever is the earlier time, say Q1 is the earlier time, so 1 is the earlier time. Please measure Q, the observable Q, then evolve a little bit further, and then please measure Q at that later time again. And take the outcomes at time 1, take the outcomes at time 2, multiply them just as you would do classically, sorry. Take the product, and for each individual measurement run, this product will be either plus or minus 1. But now repeat the whole thing many, many times to get statistics, then take the average over these many times. That's your correlator. So you do exactly the same thing that you would also do classically. But of course, the trick why you don't get the same why you don't fulfill Leggett-Garg inequality, the trick is, of course, that these assumptions are wrong. The quantum mechanics does, the measurement does affect subsequent measurements, and the observables cannot be assumed simply to have definite values even without a measurement at any time, and so on. Okay, you're welcome. Okay, good. Good, back to decoherence. I was just saying decoherence on the simplest level is just loss of interference. So what I like to imagine when I start talking about decoherence is a very simple interference experiment where I say I have 2 wave packets. Maybe they resulted from 1 wave packet that was split into 2. They are traveling along different trajectories as shown here. And then I make these trajectories bend around. Maybe I deflect these wave packets from a potential or something. And when these wave packets start to overlap, it turns out that I see interference fringes. So here I displayed them in this 2D picture. So these lines are lines of probability density being suppressed and going down to 0. But I can also make a cut. So what I can imagine is that I take a cut along this 1D line, and then I plot the probability density along this 1D 1D line. So that is X and that is also X. And then I will see these interference fringes, these characteristic zeros in particular in the interference pattern that results. Okay. And if I wanted to calculate it, it's also pretty easy. I would say, okay, psi of X, I could represent it as a superposition of psi up and psi down, say with 1 over square root of 2, because they are both normalized, and I want also to make sure the whole thing is normalized. And then what I find is that the square of this, of course, has these simple terms where I only take psi up squared and psi down squared. And the sum of those probability densities, that's kind of what you would expect even in a classical experiment where you don't know about interference. But then there are these extra terms where you have to multiply psi up star with psi down and the other way around. And these are the interference terms. They give rise to these interference fringes. So very simple. Now, one important thing is that these interference terms are very sensitive to the relative phase. So if I were to take psi up and multiply it by some phase factor e to the I phi, then these first two terms on the right-hand side would not change, but the interference terms, they would change. And what it would mean physically is that this interference pattern could actually shift around. That's what a phase difference would mean in terms of what you observe. Okay. Now, this is not yet decoherence, this is just interference. But the question is, what happens now if I add noise? If I add noise, so I might have a noisy fluctuating field, say in one arm of the interferometer. And what this could mean for me is that there's a phase shift that I acquire because of this noisy field. At least this is the least that can happen. I could also deflect the wave packets and the trajectories, but that's more complicated. At least I can get a new phase shift. I can call this phase shift e to the I phi. And I've inserted it for you already here down there at the interference terms. Now this alone, again, would not do something bad. But the reason that something bad happens is, even if in a single run of the experiment I get a definite phase shift, in the next time I try the experiment, I get a slightly different phase shift because this is noise, not just some deterministic field. Now, in order to acquire this psi of x squared probability density, what I really have to do is I have to average it over many runs of the experiment. I have to send through many wave packets through my experiment. And so I have to average the e to the I phi term. And if I do that, I get a number of magnitude less than unity. Yeah? So e to the I phi still has magnitude unity, is a complex number, but magnitude unity. But if I average it over a fluctuating value of phi, I get a number less than 1. If I get a number less of 1, I suppress the interference term. If I suppress the interference term, I go closer to what I would expect classically. And what I would expect classically is just a very boring looking, well, sum of two Gaussians type of curve. So I suppress the interference term, I see less of the interference fringes. This is decoherence in a nutshell. Yeah? So you have interference, it relies on phase coherence. If I add noise, for example, by a noisy fluctuating field, I get noisy phase shifts. If I average over the noisy phase shifts, I suppress interference terms. And so I get closer and closer to the classical outcome. Okay, so that is decoherence in a nutshell. But now we want to describe it with reference to the full quantum mechanical description. Here I describe it as being classical noise and extra phase shift coming in. But there's a more quantum version of describing the same thing. And this will also bring in, again, the pointer states. And so this is the first thing that we are going to discuss. And it brings us right back to measurement, actually. So I labeled this subsection decoherence versus information gain. Because what we will see is this loss of coherence, this destruction of interference, in a measurement, while a measurement is going on, is connected to how much information I gain about my system state. The more information I gain, the more decoherence there must be. Okay. Now we start very simple again. We say that we look at the usual measurement, think of the Stern-Gerlach apparatus if you like, and we now look at the state, maybe not at the final point in time where the two pointer states are orthogonal, but at some intermediate time, as shown here. Still, the overall structure of the state is the same as before, up times chi up, down times chi down, superposition of these two, typical entangled state. But what I will assume now is that chi up and chi down, they are not yet completely orthogonal. So graphically speaking, I could really draw them like vectors in a Hilbert space, and the angle between them is not yet 90 degrees. Now we will have two questions. The first question is, how much are the interference effects suppressed? So how much of decoherence do we have? And the second question will be, how much did we actually learn about the system state indirectly from the pointer states? So these are the two questions that we want to answer. In the end, we will see that they are connected. So decoherence connected to information gain. Let's try to answer them one by one. So how much are the interference effects suppressed? How can I quantify this? Well, I have to look at, so now I'm not talking only about this two-level system, spin up and spin down. I'm not talking about this nice wave packets and interference fringes in real space. But I can still try to look at some observable that is sensitive to the relative phase between up and down. Now, it would be stupid to measure, for example, sigma z, because sigma z is not sensitive to the relative phase. But it is very smart to measure sigma x, because sigma x is exactly an observable that is sensitive to the relative phase. So if I calculate the expectation value of sigma x in the state psi of the overall system, so psi includes both the up and down, the system state, and the apparatus state as well. If I calculate the expectation value of sigma x, then so two things happen. First, sigma x, of course, only acts on the system state, the up versus down. Actually, it flips up into down. So sigma x applied to up is just down, and also the other way around. So you need this in order to calculate this here. And that gives rise to terms which actually connect up with down. And so you end up with terms that have a contribution both from alpha and from beta. And this is why they are sensitive to the phase. The second thing that happens is, if I already take into account the apparatus state, is that you get the overlap between chi up and chi down. So this overlap between chi up and chi down is exactly analogous now to what I had earlier in terms of this average phase shift factor e to the I phi. So now it's the overlap between chi up and chi down, the pointer state overlap. And we might call this the coherence factor in the sense that it will also be a number of magnitude less than 1, and it will suppress the size of this sigma x expectation value that is sensitive to the phase. So it suppresses the coherence. But here, as we learn, it's nothing else but the overlap of pointer states. So in order to demonstrate that we are really suppressing an interesting interference effect, let me just imagine that I have a deterministic phase shift phi. So that's not noisy, it's just deterministic. I introduce that into the initial state. And I want to calculate how the expectation value of sigma x depends on this deterministic phase phi. And if you work it out, it's like a cosine of phi. The blue curve shown here is in case of this coherence factor being 1. So if I don't have pointer states at all, if I don't do the measurement, it's just the system itself. So I get a perfect interference pattern. If, on the other hand, I do have the pointer states and C is already less than 1, then I have suppressed this nice interference pattern cosine of phi as a function of phi. So we certainly suppress interference. And the suppression is connected to this overlap of pointer states. Now we come to the second question. What about information gain? So how much do we learn about the system state? Well, learning something about the system state is the ultimate goal of this measurement, of course. And the way we should think about it here is again in the same way that we already did it for the weak measurement. So we say first there was the interaction between the system state and the pointer states, the measurement apparatus. And then in a second step, I will now imagine that I now apply a strong projective measurement on this apparatus. So I do a projective measurement of the apparatus, but since the two pointer states are not at all orthogonal, they are just a little bit apart, this extra measurement will not reveal too much information. It's exactly the story that we already learned about the weak measurements. So they are not perfectly correlated with spin. I cannot possibly learn everything there is to know. I cannot say with certainty after looking at these apparatus states whether it's up or down. It's all a matter of statistics. There's another challenge here. The challenge is now, if we want to get more quantitative, we want to choose an optimal basis for the measurement of the apparatus. We can't choose this basis chi up and chi down because that's not even a basis. At least it's not an orthogonal basis since they are not orthogonal. So we need to choose another basis that could serve as a measurement basis and which is somehow smart, so it should distinguish as much as is possible these two pointer states. So we're looking at a basis, an orthogonal basis, that is as smart as possible in distinguishing the two pointer states. And I already revealed the result. Basically, you can do a little bit of geometry yourself. What I show here in blue, that is the optimal basis. So two vectors that are orthogonal and that are kind of symmetric around the chi up and chi down. And then if I do find in my measurement, for example, if I do find chi up, optimal, so OPT means optimal measurement basis. If I do find that in a measurement that can distinguish these two measurement basis states, this is a little bit closer to chi up than it is to chi down. So I'm a little bit more likely to say, oh, maybe I'm in the up state rather than in the down state, but I cannot be completely certain. Anyway, this is the optimal measurement basis as one can work out. And I should just say that whenever I now write down formulas, I will assume for simplicity that this pointer state overlap between chi up and chi down was a real valued number and not a complex phase factor. If there is a complex phase factor between the two pointer states, I can actually pull that over to the up and the down states and make my life easier. So let me just assume that this coherence factor is now real valued just to make it easier. Okay, so there's this optimal basis, which is the smartest basis to try to distinguish as much as possible chi up versus chi down, but I will not succeed completely because they are not orthogonal. Now, what happens if I do measure in this basis? So for example, let's just imagine I do find chi up of the optimal measurement basis, so chi up optimal. What does this mean? Well, after I do this measurement, it's a projective measurement, so I should update my state in the usual, according to the usual prescription. So what I would say is I can take the original wave function, which was a joint wave function, both of system and apparatus. I project it onto this chi up optimal, onto the state that I found in my strong projective measurement of the apparatus. And what the remaining state will be if I carry out formally this overlap is it's not yet a number, it's still a state of the system. So I started from a joint state of system and apparatus, I projected it onto an apparatus state, the result is a state of the system. And then in order to make everything correct, of course, I would normalize by dividing by a proper factor, by the length of this vector. Okay, so this is the updated state of the system after I found this particular state in my measurement apparatus. And so I can now see what happens with my system state when I do this. before, so, okay, now I should specialize a little bit more to keep things simple. I will assume that the probabilities for up and down were equal, were 1/2. So it's the optimal superposition, equal superposition, really the best thing I can have in terms of superpositions. And so before I do any of this, before I do even the full measure, before I do any of the measurement, the probability to find spin up was 1/2, and the probability to find spin down was also 1/2. Okay, by assumption. But now I let my system interact with a measurement apparatus. I get this entangled state. And in addition, I now measure the state chi of the measurement apparatus. And this leads to a projective measurement. I undergo the projection that I just talked about, and I update my system state. And now the system state, the new system state, it does have a bias. Maybe I now know a little bit that I'm rather likely in the up state rather than in the down state. So this is what I just said. If I happen to find chi up optimal in this measurement that tries to distinguish this state from that state, then this is a little bit closer to chi up than to chi down. So also this means that if you go through the math, which I am not now doing here, you will find there's a preference for up. And what this means in very simple terms is just there is now a slight correlation between the apparatus state and the system state. And if you do measure the apparatus state, you do learn indirectly something about the system state. So we really have learned something about the system. Yeah, so good question. So in the double slit experiment, if you do measure which is the slit where the electron passes, you destroy interference. Can the situation be described in terms of orthogonal pointer states? Yes, absolutely. So if we have a double slit situation, so to speak, the wave packet being in the upper slit, I could call this up. The wave packet being in the lower slit, I could call this down. And now if I do a measurement, for example, by scattering of a photon, I could call the resulting state of the electromagnetic field chi up or chi down, as the case may be. And if these two states are orthogonal, which means I really have succeeded completely in figuring out whether I went through the upper slit or the lower slit, then yes, first of all, I have destroyed interference completely, but second also, I know exactly whether it's the upper or the lower slit. So it's exactly the situation. Thank you. So it's exactly what we have here. Okay, so now we know more. The only question that remains is, can we quantify this instead of just drawing these pictures and saying, aha, we have learned indirectly something about the system state. And so the question is, how do you quantify information? We have increased our information. How do we quantify this? And anyone who knows a little bit about, say, information theory, this is the first thing you learn. In order to quantify information, we need to talk about entropy. So before this measurement, the state of the system was very uncertain. It was 1/2, 1/2, up versus down. We don't know anything. Afterwards, there's a bias. We know, oh, there's a large likelihood that it is up rather than down. Not perfect, not 100%, but it's much increased. So we would say we have increased our information. And the general idea is to measure ignorance, not information, but ignorance by the entropy. The entropy is the same one you already learned in your statistical physics lectures. Sometimes in this context, it also carries the name of Shannon entropy, because Claude Shannon was the first one who applied all these concepts not to physics, but to the theory of information. And if you do that, sometimes even instead of the natural logarithm, you take the logarithm to base 2, but these are all choices. That's not so important. Anyway, so this is a measure of ignorance. It's maximum for the uniform distribution, and it's minimum, namely 0, if the distribution is centered completely 100% on one of the values. And so then we can define information gain as the decrease of ignorance, is the decrease of entropy. And so if you work it out for this example, the decrease of entropy, well, you can express it in terms of the probabilities. And if you work out these probabilities for this example, it turns out they can be expressed completely in terms of this overlap C again, the same C, the overlap of pointer states that occurs already when we discussed coherence, our coherence factor. So immediately you see that there's a direct relation between the information gain and decoherence. And this can be made even a little bit more quantitative. Let's now just assume that we're in the beginning of the measurement when this overlap is still very large, but it's already not 1 anymore. And then we can say, so we have a weak measurement, the overlap is close to 1. I can express it actually like a cosine of an angle between these two vectors. Remember, we imagined that any phase vector has already been pulled out of this. And then if the angle is small, so I'm making a weak measurement, I can expand the cosine 1 minus theta squared half. And I can then insert that into the expression for the entropy and also do an expansion of the entropy. And here's the result. So the information gain is theta squared half. The coherence factor loss is also theta squared half. And so it's just the same. The loss of one is the gain of the other. And I can even go a little bit further. I can say, oh, let me now take many little steps in the spirit of this weak measurement where I have many ancillas passing by my quantum system. Then the overlap factor after all of this has happened can actually be expressed as what happens in an individual ancilla and then to the power of n. If I have n steps and all these ancillas are identical and the interaction time is identical for each of them, I just need to raise it to the power. Otherwise, I need to take the product. And if I take the power and expand this for small theta again, this is the expression I get. So 1 minus the number of steps that I took times this theta squared half. But if I look at the information gain, I will find also something very simple, namely in each of these steps, if I'm still in the early stages of the measurement, I gain the same amount of information. And so I just get n times theta squared half. So I can draw this in a nice diagram. If I have a certain number of steps per second, then the number of ancillas passing by my system and the time, they are just proportional to each other. So I can draw literally the coherence versus time. It decreases linearly at first. And I can draw the information gain versus time. It increases. And so you really, again, directly see how it would look like for a weak measurement as we observe the continuous loss of coherence and the continuous gain in information. And once you are at this point, you can also speak of rates. So there's a rate at which the coherence decreases. If you write the loss of coherence as something like gamma times t. And there's a rate at which the information increases, again, something gamma times t. One of these rates you could call the decoherence rate. The other you could call the measurement rate. In the example we just worked out, they are actually equal. Now, if you do it in a slightly more stupid way, it might happen that the measurement rate becomes smaller than the decoherence rate. This will be true if, for example, you do not choose this optimal measurement basis that I talked about a little while earlier. If you don't choose this basis, but a stupid basis, then maybe you don't gain any information because you chose the wrong basis. And then the measurement rate would be 0, but the decoherence rate is still there because that doesn't go away. The overlap is still less than 1. So we see in the best case, they are equal. In the worst case, you don't gain any information and you still have the decoherence to pay. Okay. So this is one way of seeing this connection. And just to conclude this lecture today, I want to advertise a slightly different perspective. So one of the things we just noticed is this coherence factor is the overlap. The entropy is a more complicated function of the overlap that involves logarithms. So they are not quite the same. They only become simple looking if I'm at the early stages of a weak measurement, and then I can do what I did here. If I want to go further and make a tight connection, maybe it would be good if even this loss of coherence could be described a little bit in terms of something like an entropy. But the question is, how do I bring in an entropy to describe this loss of coherence? And so the idea is this can actually be done. And this new perspective also gives rise to a nice new relation of this loss of coherence and the information gain to something else, namely the entanglement between system and apparatus. So here's the new perspective. Let me again assume for simplicity, but all of this can be generalized. We're starting with a simple equal superposition state. So that would be an eigenstate of the sigma x operator. And now if I look at the probabilities not in the sigma z basis, up and down were 50-50, but actually in the sigma x basis, then this eigenstate has 100%. So this is 100%, and the other eigenstate of sigma x has 0%. And this is an interesting way to look at it, because it's a pure state, and it's a pure state exactly in the sigma. It's a pure state overall, but it's also an eigenstate of sigma x. So here it's revealed that this, so this is a perfectly well-defined state. Now what happens as the measurement goes on, as you interact with this measurement apparatus, is if you calculate at the end of time, when this overlap of pointer states is already very small, if you calculate the probabilities to find the system in either one of the sigma x eigenstates, you actually find something close to 50-50, or eventually in the limit of infinite time when the pointer states are orthogonal, it's 50-50. And so what has happened here is really that out of a coherent pure state, you ended up in a completely incoherent mixture. So in any basis you choose now, it will be 50-50. If you calculate the probabilities in the sigma z basis, up versus down, it's 50-50. Sigma x basis, the same thing, 50-50. Sigma y basis, 50-50. It's completely incoherent classical mixture of states, no superposition anymore, not sensitive to any phase. So in this way now, we can, since we're talking about probabilities, we can also look at the entropy. And we could say initially, the entropy was 0. The entropy of this probability distribution was 0, which was connected to the fact that it was a pure state. In the end, this entropy is maximum because it's just 50-50. So what I just said, the system state becomes an incoherent mixture eventually as time goes on, and therefore its entropy actually increases. Yeah. Now that's the system state where I don't condition on the apparatus state. So I don't do what I did before. So I just look, I close my eyes, I don't look at the apparatus, I only look at the system, I find that it becomes a completely incoherent mixture. But now if I do look at the apparatus and look at the system state conditioned on the outcome of my apparatus measurement, that is of course the thing we discussed already. That conditioned system state, conditioned on the apparatus state, becomes more certain. So that entropy decreases. That's what we discussed before. So we are now dealing with different entropies. It's the entropy of the conditional state, conditioned on the apparatus pointer state, and it's the overall entropy of the system state if I do not do this conditioning. And this overall entropy, the fact that this increases tells us that we're going to this incoherent mixture. So that's another perspective. And here it's just in a nutshell. I have initially this nice superposition of up and down, and it's in a product state with my initial pointer state here is 0. But as time goes on, I'm entangling the system and the measurement apparatus. And now afterwards, there will be a strong correlation between the system state and the measurement apparatus state. So if the measurement apparatus state is high up, the system state is up. If it's high down, the system state is down. So this is what happens there, the strong correlation. So that also means information gain. So if I now measure the apparatus, I know what must be the system state. So that's the good thing. So there are two things. First, we have this really big information gain. And the second thing is also the system and the apparatus become entangled, because that's what happens. And they become perfectly entangled after a while. The other thing is the one that we just discussed. So if I only look at a subsystem, if I only look at my up versus down, my little quantum system, that becomes incoherent. And also the entropy of the state becomes high. And so this, these things are all related. And the reason they are related is what I'm doing now here, looking at the entropy of a subsystem of an overall joint system, that is actually a way to quantify entanglement between the two systems. So in this case, entanglement between our little system and the measurement apparatus. So for pure joint states, looking at the entanglement of a subsystem is a way to quantify entanglement. So now we know, now we understand why these things are necessarily why they go together. So as system and apparatus become more and more entangled, that's good for the information gain because their states become more strongly correlated. But at the same time, because of this entanglement, the entropy of the subsystem increases. It becomes more incoherent, it becomes more of a mixed state, and therefore also the coherence, the interference effects, they go away. Okay. So this is, I guess, I'm already a little bit over time. This is what I wanted to tell you today, information gain versus coherence. And so next week, we will continue and finish the decoherence chapter. And we finally come to the favorite of you all. That's the Schrödinger cat as an example of macroscopic, so-called macroscopic superposition states. And we will say something about how should we describe the decoherence of these states? Why are they so fragile? Why is it so hard to see these states? And then after we've discussed this, then we will switch to interpretations of quantum mechanics, and we will start to discuss things like Bohm's pilot wave theory. So that's also extremely interesting. Now again, we're a little bit over time, but if there's any question, we still have 2 minutes or so to answer that. Okay. Still a short announcement. You know that on the website, there's the new problem set, 3 interesting problems. And I think we will arrange the little tutorial actually next week, not this week, but next week. And I alert you to the time on the Google Groups. Okay, with that, maybe it's enough for today. It was fun to have you here again, and see you next time. See you next Monday.